Hi everyone, I'm Neil and I'm a grad student at Carnegie Mellon, and today I'm going to talk about my joint work with Aaditya Ramdas on dynamic algorithms for online multiple testing. So first I'm going to talk a little bit about the problem of online multiple testing before we dive into our contributions into the topic. So fundamentally what it's about is about testing many different hypotheses. Imagine we're a tech company and we're interested in what kind of features on our web page would affect user engagement. So one hypothesis is that the color of our web page affects it. Another might be the number of icons. Another might be the style of the web page. And ultimately our goal is to reject as many non-null hypotheses as possible, which means that we want to find as many hypotheses where it does truly affect our user engagement levels. And the analogy in kind of science is that we want to find all the hypotheses where the null hypothesis is wrong, and we're making some true discoveries, true novel discoveries about the world, essentially. So to formalize this problem, we start with hypotheses, and for hypotheses, we perform some experiment testing this hypothesis, and we get a p-value, which is a statistic that summarizes kind of the empirical evidence for a hypothesis. And then what our algorithm does is that it then outputs an alpha value without looking at the p-value, and this is our threshold for rejection. So if the p-value is less than this alpha value, then we reject this hypothesis, otherwise we don't. And we continue with this infinite stream of hypotheses and p-values and outputting rejection thresholds. And this is why it's an online problem, because there's an infinite stream of these. So to talk a little bit about p-values, there are statistics that are supported on 0, 1 that essentially summarize evidence for a hypothesis. So specifically, p-values have this called superuniformity property if the hypothesis associated with the p-value is null. So this includes essentially having the p-value being uniformly distributed on 0, 1. Otherwise, we don't know the distribution of the p-value if the hypothesis is not null, but we would hope it is small, because from the previous setup, we can see that we generally reject hypotheses where the p-values are small. Consequently, small p-values provide more evidence against the null hypothesis. And if we do end up rejecting a p-value where the hypothesis is null, we call this a false discovery, because it's the hypothesis itself is not non-null, it's truly null, but we still reject it. So the key error metrics we wish to keep controlled that in this problem all concern this thing called the false discovery proportion, or FTP, which is the proportion of the number of discoveries we make by time k that are false. So we rejected a null hypothesis instead of a non-null hypothesis. And generally, prior work has looked at the expectation of this value. So they've looked at the false discovery rate, FDR, which is kind of the largest expectation of the FTP at a fixed time. Instead, we thought maybe we might be interested in kind of the tail of the FTP. So maybe we're looking at a probabilistic bound. So we look at a metric called the FDX, or false discovery exceedance, where we look at the probability that the false discovery proportion exceeds some threshold. So a key difference between this and FDR is that we're looking at a time uniform bound. So the probability at any time step after some specific time step, or random time, large k, that our false discovery proportion exceeds this threshold epsilon. And we also kind of look at this augmented version of the FDR, where we're not just considering the largest expectation over all fixed times, but also data-dependent stopping times. So we do it over stopping times, and stopping times are essentially if the time is dependent on the data we've gathered already. So maybe stopping at, let's say, the fifth rejection is a stopping time, or stopping, once our budget is exhausted, if we have some real life cost budget. These are all kind of based on the data. So our algorithm is in charge of controlling both FDX and FDR, and this augmented notion of FDR with stopping times. So to do this, we use this paradigm for designing algorithms for the online multiple testing problem called alpha investing. So we start with some wealth. Each algorithm starts with some wealth. And whenever it outputs an alpha value, it spends wealth to output that alpha value. And it gains wealth when we actually make a rejection. and this just continues onwards. So the idea behind these types of algorithms is that we want to ensure that when there's non-zero wealth, it's the same thing as saying our desired error metric is being controlled, whether that's FDR or FDX. And we also want to maximize our power, which is the number of true discoveries divided by the total number of non-null hypotheses. So we want to maximize the percentage of non-null hypotheses that we end up rejecting, because those are the ones we want to discover. So ultimately our goal is to have algorithms with high power that ensure that either the FDX or FDR is controlled under a fixed level. So our contributions, the first is that we present the first practically powerful algorithm with FDX control. There are prior algorithms that do provide FDX control, but we show that our algorithm vastly outperforms them and that the previous algorithms actually don't outcompete some very basic baselines. And secondly, we present a method for dynamically allocating our alpha values that improves power over prior methods. Lastly, we also show essentially the first method for controlling FDR at stopping times, but we'll defer this point to the paper if you want to look at the details. So to introduce how we can guarantee provable control of the FDX, first we're going to talk about this estimator view of the FTP. So we're rewriting the FTP here, where in the numerator we're counting all the hypotheses that are null and have been rejected, which means the p-value is less than or equal to alpha. And we're also going to present what's called an estimator of the FTP. So instead of indicator variables in the numerator, we just have the sum of alpha values. And Ramdas et al. In 2017 proved this theorem where it shows that in expectation, the FTP is smaller than the FTP hat, often conditional on the past rejections. And this algorithm LORD, which was first introduced by Javimard and Montanari, basically ensures that FTP hat is less than or equal to this fixed level L for all time steps, for all k and n. So these two facts combined essentially give us that LORD can control FDR at level L, just because it controls this estimator at level L. So we try to accomplish something similar for the probabilistic bound. So Katsovich and Ramdas in 2021 designed this high probability estimator of the FTP called FTP Bar. So basically, FTP only exceeds FTP Bar at any time with probability less than or equal to delta, so some fixed level. So this is a high probability bound at FTP. So FTP Bar kind of looks like this, where part of it kind of looks like FTP hat because we have sum of alphas in the numerator and number of rejections in the denominator, and it's increased by this approximately log function of 1 over delta. So this numerator denominator split kind of explains how this correlates to wealth, because when we output an alpha value, we increase FTP bar, so it's closer to our threshold of we require FTP bar to be less than epsilon, and that decreases our wealth. Simultaneously, if we're making rejection, we're increasing the denominator here, which decreases FTP bar, and consequently that increases wealth because that's expanding the gap between our threshold epsilon and FTP bar, which is required to be below epsilon. And this is the theorem we show, is that if you keep FTP bar below epsilon at all rejection times after large K, so it doesn't need to be all times, just all the times where we actually reject a hypothesis after large K, this is the same as controlling FDX to be less than or equal to delta, because of the fact that the true FTP only exceeds this estimator FTP with probability less than or equal to delta. So sup LORD simply makes sure that FTP bar is controlled to be under epsilon, just like LORD made sure FTP hat was under L. And we now can look at some numerical simulations where we show that sup LORD does better than prior algorithms. So our simulation is to produce p-values from a one-sided z-test on IID Gaussians, where the null has 0 mean and the non-null has different means. And we just choose these settings for our FDX in the top row and our FDR controlling algorithms in the bottom row, because I guess there's no explicit way to compare them, and these seem like reasonable parameters to choose for each. So here we have a graph of power against the performance of our algorithms, both some baseline Lord algorithms, Bonferroni, which is essentially the sum of the alpha values is controlled to be less than L, and also Lord FDX, which is the prior algorithm for controlling FDX based on Lord. So mu represents the mean of the non-nulls, and pi represents the rate at which non-nulls occur. So the higher the pi, the more non-nulls there are. So we look at this prior FDX controlling method based on Lord, and its performance is quite bad. It does even worse than Bonferroni, versus our method, which is much better and does better than Lord with this parameter choice, but essentially has non-negligible power. We also run this all these algorithms on a real-world data set, and we show that our algorithm makes the most rejections, which does not necessarily mean it has the most power, but this reflects the notion that it's a powerful algorithm. So to talk about our second contribution about dynamic assignment of alpha values, we're going to dive into the definition of wealth explicitly for our algorithm SUPLORD. So we define wealth this way, and essentially what we're saying wealth is how much can the algorithm spend before FTP Bar exceeds this threshold epsilon. And if we graph the wealth of our algorithm over multiple trials, we can see that here our average wealth that SUPLORD accumulates is actually increasing over the more hypotheses it tests, the more wealth it accumulates. And this is kind of bad because this is unused wealth, which means we have smaller alpha values than we could have had, and then that means we have some unexploited power here. So we could have more powerful algorithms if we just increased our alpha values a little more and used up this wealth. So really the solution here is just to make larger alpha values that are also uniform in size. So here we have our algorithm, the new dynamic allocation of alpha values in purple. And we can see that it generally has larger alpha values than the red, which is the previous non-dynamic algorithm, and blue, which is also an algorithm that uses up a lot of wealth, but uses it in very heavily in a few spots. So we show that spreading it out seems to produce higher alpha values in general, which is the point of our algorithm. And of course, here we can see our purple algorithm no longer has increasing wealth. And if we actually plot the power of our algorithms, we see that, okay, our purple dynamic algorithm does have more power than the other two baselines. So our takeaways are, first, that FDX control can be achieved using a high probability estimator of the FTP. And this estimator is non-trivial. It does give us a powerful algorithm that's more powerful than prior methods. And secondly, that previous algorithms had this underutilization of wealth, that there were some free wealth that we could convert into larger alpha values that could just increase the power of our algorithm more. So we can use that. So that's it. Thanks for listening.